Good morning. I'm getting bored, so I listen. So let's do something in the night, in the morning. Okay. So consider the small fluid element length ds cross section dA along the streamline, force acting along the streamline, pressure force bracket 1 P minus bracket 1 P plus dP into the dA equal to the minus dP into the dA, and a weight component rho g dA ds cos theta acceleration force rho dA ds dot as from the Newton's second law. Sum of the forces equal to the mass into accelerations minus dp into dA minus rho g dA ds cos theta equal to the rho dA ds into the as divided by the rho dA ds. So bracket 1 dp by the d rho dp by the rho plus g dz plus as ds equal to the 0. This is the Euler's equations of motions. Now Euler's equations in different directions along the streamline dp by the rho plus g dz plus v dv equal to the 0 in the vertical directions. In the vertical direction, static fluids dp divided by the dz equal to the minus rho g. This reduces to the hydrostatic law. Bernoulli's equations integrated Euler's equation integral dp divided by the p plus integral g dz plus integral v dv equal to the 0, p divided by the rho plus g into z plus v square divided by 2 equal to the constant in the head form. P divided by the rho g plus z plus v square divided by the 2g equal to the constant. Physical meaning term. P divided by rho g is the pressure head, z is the elevation head, v square divided by 2z velocity head. Navier-Stokes equations, real fluid advance, general form. General form vector rho bracket 1 dv vector divided by dt plus v vector dot del bracket 1 v vector equal to the minus Laplace p plus mu into the Laplace square v vector plus rho g vector. And now the static fluid v equal to the 0, therefore dp divided by the dz equal to the minus rho g. Horizontal flow dz equal to the 0, p divided by the rho plus v square divided by the 2 equal to the constant. Stagnation points v equal to the 0, therefore the p equal to the p max. So now let's deal some numerical. Euler to the Bernoullis. At the point in the pipe, pressure 200 kPa, velocity 5 meter per second, elevation 10 meter, and find the total head. P divided by the rho g 2 lakh divided by the 1000 into 9.81 20.39 meter. V square divided by 2z equal 25 divided by 19.62 1.27 meter. H equal to 20.39 plus 10 plus 1.27, H equal to the 31.66 meter. Now, second one is the stagnation pressure, velocity of the air 30 meter per second, the density 1.2 kilogram per meter cube. Find the stagnation pressure, right? Delta P equal to the 1 divided by the 2 rho V square 0.5 into the 1.2 into 30 square 540 Pascal. And let's further deal some interesting one. Now Bernoulli's equation, and at a point in the horizontal pipe, pressure is 300 kPa, velocity 4 meter per second. Find total head at that point. Rho equal to the 1000 kilogram per meter cube, g 9.81 meter per second square, Pressure head P divided by the rho g 3 lakh divided by the 1000 into 9.81 30.58 meter. Velocity head is the v square divided by the 2g 16 divided by the 19.62 0.82 meter. Since the pipe is the horizontal and z is equal to the 0, the h equal to the 30.58 plus 0.82 and h is the 31.4 meter. The pressure changes using the Bernoullis. The water flow in the pipe velocity increases from the 3 meter per second to the 7 meter per second. Find the pressure drop. Now Bernoulli's horizontal flow P1 by the rho plus V1 square divided by 2 equal to the P2 divided by the rho plus V2 square by the 2. P1 minus P2 equal to the rho divided by the 2 bracket 1 V2 square minus V1 square and 1000 divided by 2 49 minus 9 equal to the 500. 500 into the 40 P1 minus P2 equal to the 20,000 Pascal 20 kPascal. Stagnation pressure velocity air is the 40 meter per second, density air 1.2 kilogram per meter cube. Find the stagnation pressure rise. Solution delta P equal to the 1 divided by 2 rho V square 0.5 into the 1.2 into the 40 square 960 Pascal. Delta P is the 0.96 K Pascal. Euler's equations Euler's equations hydrostatics. Find the pressure at the depth 6 meter below free surface of the water. From the Euler's static fluid, dP divided by the dz equal to the minus rho g P equal to the rho g h 1000 into 9.81 into the 6 P equal to the 58.86 K Pascal. Vertical flow Bernoullis with the elevations. Water flows upward in the pipeline at the point A, pressure 250 kPa, velocity 2 meter per second, elevation 0. At the point B, velocity 5 meter per second and elevation 8 meter. Find the pressure at the B. Solution Bernoullis Pa divided by the rho g plus Va square divided by 2z plus Za equal to the Pb divided by the rho g plus Vb square divided by the 2z and plus Zb. So 2 lakh 50,000 by 9,810 plus 4 divided by the 19.62 equal to the PB divided by the 9,810 plus 25 divided by the 19.62 plus 8. 25.48 plus 0.204 equal to the PB by the 9,810 plus 1.275 plus 8. PB divided by the 9,810 equal to the 16.41. PB equal to the 1,61,000 Pascal. PV equal to the 161 K Pascal. Acceleration along the streamline. Euler's equation. Velocity of the water increases from the 2 meter per second to the 6 meter per second over a distance of the 4 meter. Find the acceleration along the streamline. Let's as equal to the v into the dv by the ds. dv divided by the ds 6 minus 2 divided by the 4 1 per second. Average velocity v average equal to the 2 plus 6 divided by 2 equal to the 4. As equal to the 4 into the 1. As equal to the 4 meter per second square. Bernoulli's validity check. Water flows with the velocity 10 meter per second and the head loss is the 3 meter. If the Bernoulli's head is the 25 meter, find the actual head. Solution therefore H actual equal to the H Bernoulli minus HL. 25 minus 3, H actual equal to the 22 meter. Navier-Stokes conceptual numerical. Okay. So for a static fluid, velocity equal to the zero, what does Navier-Stokes reduce to? dP divided by dz equal to the minus rho g hydrostatic equations. Now let's deal some more. Hey, accelerating the flow Euler equation. Velocity along the streamline varies as v equal to the 3x square meter per second. X distance meters, find acceleration x equal to 2 meter, solution a equal to the v into the dv divided by dx, and dv divided by dx equal to the 6x. At the x equal to the 2, v equal to the 3 into the 2 square equal to 12 meter per second, and dv divided by dx equal to the 12. A equal to the 12 into 12 equal to the 144 meter per second square. Pressure gradient from the Euler's equations. Water flows horizontally with the velocity distribution v equal to 5x meter per second. Find the pressure gradient at the x equal to the 1 meter. You therefore the Euler's equations dp divided by the dx equal to the minus rho v into the dv by the dx, and dv by the dx equal to the 5 at the x equal to the 1, and v at the x equal to the 1 and v equal to the 5. So therefore dp by the dx equal to the minus 1000 into the 5 into the 5, dp divided by dx equal to the minus 25,000 Pascal per meter. Vertical flow with the acceleration. Water flows vertically upward with the velocity changing from 2 meter per second to the 6 meter per second over the 5 meter height. Find the pressure drop. Bernoulli's Bernoulli plus elevation. Bernoulli plus elevation P1 divided by the rho g plus V1 square divided by 2z equal to the P2 divided by the rho g plus V2 square divided by 2z and plus z. So therefore, the P1 minus P2 divided by the rho g equal to the 36 minus 4 divided by the 19.62 plus 5. 1.63 plus 5 equal to the 6.63. P1 minus P2. P1 minus P2 equal to the P1 minus P2 equal to 1000 into the 9.81 into the 6.63. Therefore, the P1 minus P2 equal to the 65.1 K Pascal. Now the stagnation point on the moving stream. Water velocity 15 meter per second. Static pressure will be the 120 kPa. Find the stagnation pressure. Solution P naught equal to the P plus 1 by 2 rho V square. Now the 1,20,000 plus 0.5 into the 1000 into the 15 square. So 1,20,000 plus 1,12,500 P naught equal to the 232.5 kPa. So energy line and a hydraulic grid line at a section of the pipe. Pressure is the 200 kPa, velocity is 6 meter per second, elevation is the 4 meter. Find the HGL and EGL. Pressure head P divided by the rho G 2 lakh divided by 9,810 20.39 meter. Velocity head 36 upon 19.6 to 1.84 meter hydraulic gradient line. 20.39 plus 4, 24.39, and EGL. EGL and 24.39 plus 1.84, that is 26.23 meter. Head loss inclusion. Bernoulli's head between the 2 points equal to the 40 meter and head loss is the 7 meter. Find the actual energy head. Actual equal to the 40 minus 7 33 meter. Pressure variations in accelerating fluid. Pressure variations in accelerating fluid. Fluid in a container accelerates upwards at the 3 meter per second square. Find the effective pressure gradient. Effective gravity, if I find the effective pressure gradient. Effective gravity, therefore G effective equal to the G plus A, 9.81 plus 3, 12.81 dp divided by the dp divided by the dz equal to the rho G effective. Therefore, dp divided by the dz equal to the 12,810 Pascal per meter. Navier-Stokes simplifications. Now for the steady, incompressible, and inviscid flow. Navier-Stokes simplification. For steady, incompressible, inviscid flow, Navier-Stokes equations reduces to the Euler's equations for steady plus inviscid along the streamline Bernoulli's equations. A equal to V into dV by ds, P naught P plus equal to P plus 1 by 2 rho V square, HGL P by rho G plus Z, EGL equal to the HGL plus V square by 2Z, and acceleration frame G effective equal to the G plus minus A. Okay, thanks. Okay, thanks.